we've talked all semester about classical physics. And classical physics is, depending on who you want to credit, I mean, if you want to credit Galileo with the discovery of the law of inertia, it starts in, well, let's say 1600 to round it off. Newton is 1687 as the Principia. And classical physics really, depending on when you want to sound its death knell, is physics up until, let's say, 1850 to 1900. And what I wanted to talk about today are sort of where the inadequacies of classical physics are, and to sort of point the direction into some of the future science classes, physics classes here at Lang, where we look at some of the later developments in physics through the latter half of the 19th and the first half of the 20th century. Let's review the Newtonian paradigm, I guess we can refer to it, as for how you go about measuring things about the world. The first thing that Newton assumes is that everything, and by everything Newton really means everything, including things like light, is made of little particles. Newton characterizes these particles as in his book Optics as being infinitely hard and indivisible. They correspond to what we today would call atoms. Now nowadays we know atoms aren't the smallest particles, there are smaller particles than atoms, but we do believe, for example, that that there are smallest particles in nature. To Newton, these particles would describe everything from matter to light, and so that a description of nature is a description of what particles exist in nature and what they're doing. In order to describe what particles are doing, you first specify their locations in space. So we have to know where things are. And we have to specify their velocities, how fast they're going. If you know where particles are and how fast they're going, and there are no forces acting on them, then Newton's first law just tells you where they're going to be in the future. They're going to move in a straight line forever and ever and ever and ever. If there are forces, then Newton's laws tell you what's going to happen to them. The law of inertia. F equals ma. And the fact that forces are always equal and opposite. They're interactions between particles. Applying Newton's three laws of motion to particles requires knowing the forces on them. So we have to know how forces work. If you know the force on the particle, you can calculate its acceleration. If you know its acceleration, you know how its velocity changes. If you know how its velocity changes, you know where it's going to be in the future. So this allows us to calculate the trajectory if we know what the forces are on the particle. There are different kinds of forces under Newton. There are contact forces. You can actually just push something and exert a force on it, and that's pretty well understood. But there are also forces like gravity. And it's important to remind ourselves what Newton says about gravity, or doesn't say about gravity, in the Principia, which is that he specifically goes out of his way to state that he doesn't have any hypotheses about how gravity works or what gravity is. It's clear to Newton that, that gravity acts over some large distance. It's fairly clear, although you have to read between the lines to get at this, to Newton, that gravity acts instantaneously. In other words, if you've got the Earth going around the sun, oh sorry, let's do the moon going around the Earth. If you've got the moon going around the Earth, it's traveling in an orbit because the attractive force of gravity is always deflecting it from the path it wants to travel, which is a straight line. We call that force a centripetal force, a force which pulls you into a circle when what you really want to do is follow Newton's first law and go straight. If this is caused by gravity, which Newton says it is, the presumption is if you turned that force off by, say, just somehow magically causing the Earth to disappear, that the moon would fly off and follow Newton's first law of motion. There's nothing in Newton's law of gravitation that has to do with time. It just says that the force is G m over r squared. Presumably, if the mass is gone, the force is gone. It doesn't say anything about the time it takes that force to get from one place to another. So Newton would say if you made the Earth disappear, the moon would instantaneously fly off into space. So forces like gravity act instantaneously over space. And we are, for the time being, at least for Newton's time being, ignorant of the true cause of gravity. But given, well, and there's another statement in Newton's optics, which is really just an illusion. Newton isn't ready to attack this question yet, but he sets forward the idea that other forces, like the electrical force and the magnetic force, which were certainly known about in Newton's time, are similar in some way to gravity. So we expect other forces like electricity, magnetism, etc., should be similar to gravity. Doesn't come, well, he says that we don't know anything about them yet, but the implication he gives is when we do, we should be able to do just the same thing we do with gravity. We know an object is here, an object is here, we calculate the force, we figure out where the thing's going to go. So knowing the locations of particles, the forces on them, based on some quantitative force laws, we apply Newton's third law. And what we calculate, remember, is a trajectory. We know the where the particle is going, we know the force on it, so we know where it's going to go next, we know where it's going to go next, we know where it's going to go next, we know where it's going to go next. And so what this allows us to calculate over time is a path through space which is completely determined by the initial location and the initial velocities. Now what we discovered in the 1700s was that that was not always easy to do. It's not always easy to calculate a trajectory because it's not always easy to know all the forces on a particle. And if there are lots and lots and lots of forces on a particle,